Hello, this is Mr. Gilmore with the 5.4, the Triangle Inequality lesson. Now, my philosophy is this, that if something can be proven, let's prove it. Now, it is obvious that if we took two sides of a triangle and we added their measures together, it would be greater than the third side. But let's not consider this a postulate. Let's actually prove this today. Let me start off with a very simple question. Imagine that I give you 2 points, point A and point B. My question is, if you were standing on point A, and I put a large pile of cash on point B, what would be then the path you would take to get from point A to point B? Well, isn't it obvious? You would take the path straight from point A to point B. All right? So that's a pretty obvious path that you're going to obviously walk from point A to point B, or really run from point A to point B, because there's a large pile of cash sitting there. But let's add then a third point. So now I've actually created two paths. There's the path where you go from point A to point B, but there's another path you could take to get to point B. Instead, what if you took a path from point A to point C first, and then you walked to point B? Wouldn't it then obviously be longer to walk from point A to C and then C to B? Yeah, it would be, instead of walking from straight from point A to point B. What we're looking at then is setting up the idea of this next theorem. Now, yes, it does seem obvious. However, my philosophy is, if we can prove it, let's prove it. Okay, if it can be proven, let's prove it. What we're going to prove is that if you pick any two sides of a triangle and add them together, it will be greater than the length of the third side. We call this the triangle inequality. Let's take a look at its conditional. In a triangle, the sum, right, not just the measures of the sides, but the sum, right? We're adding lengths together. The sum of the lengths of any two sides must be greater than the length of the third side. This is again called the triangle inequality, and this is something that we're going to prove, that if you pick any two sides of a triangle and add them together, it will be greater than the third. Now, we're going to show it for one case where we're going to pick specifically two sides of a triangle, show that's greater than the third. But in a similar fashion, we could show that if we picked any two sides of that triangle, it would indeed be greater than the third side. So this is our proof setup. I'm giving you triangle ABC, right? That's it. There's nothing special about this triangle. It's very much like how we proved the triangle angle sum theorem, where we want this average Joe Mama triangle with nothing special about it. We don't know anything about its angles, anything about its sides, simply that this triangle exists. We're going to pick the two sides AC and BC. So we're going to add AC plus BC together, and we're going to prove that it's greater than AB. Okay, that the sum of these two sides, AC and BC, are going to be greater than the third side, AB. Now, I will warn you, this is a tricky proof, which is why I have set it up as a guided proof. Okay, I'm going to guide you through this. So here in a few slides, you're going to see that I provided the statements and ask the question why. You're going to help me fill in the reasons. Alrighty? Now, where this proof actually begins is it begins with a construction. Here's what we're actually going to do. We're going to take point C here in our diagram, and the segment BC is formed on a line. We're going to extend BC through that point C out to a point D. And that point that we reach as D is going to be a certain length. We're going to make it such that AC and this new segment CD are equal in length. And then what we'll do is connect A to D, forming a new triangle. Let's take a look at our construction. So with our triangle ABC, we extend the side or the segment BC out through point C to a given point D. However, this point D is a certain length from CD. In fact, we want it to be the same length of the length of AC. So in other words, CD and AC are equal in length, and we've marked those. Okay, and then we're going to connect point A to point D. All right, forming this new triangle. And in fact, what we have is we have our original triangle ABC, we have this new triangle ACD, and then we have the entire triangle ABD. Okay, ABD. Now, I have labeled angles as such, right? Take a look at where our angles are labeled. Go ahead and do the same thing as well. That BAC is angle 1, CAD is angle 2, and CDA is angle 3. It's going to help cut down on some of the three-letter angle names because we don't, again, it's a tricky proof. We don't want to get caught up in the little details, okay? So label them as angle 1, 2, and 3. It's going to help us within our proof. Let's jump into then where our proof picks up. So after our construction, we know that AC is equal to CD. Okay, that's by our construction that we have so far. So now let's jump into our next step. I'm claiming now that angle 2 and angle 3 are equal. Why am I able to do that? Well, if you take a look, triangle ACD is now an isosceles triangle. And we can then claim that the base angles are obviously equal to each other by ITT, the isosceles triangle theorem. Now let's take a look then at another angle, angle BAD. So now we're considering the entire angle BAD. Well, the entire angle BAD, because of our construction now, actually is the sum of two smaller angles, angle 1 and angle 2. Why is that? Well, that's just simply the angle addition postulate. That angle 1 and angle 2 are formed adjacent to each other, which then means that the sum of those two measures is equal to the whole measure BAD. Now I can claim that the measure of angle BAD is greater than angle 2. Why? Because we can satisfy that with the definition of greater than. Recall what definition of greater than says, that when we have the whole equal to the sum of the parts, we can then claim that the whole is always greater than the part. Okay, that's the definition of what greater than is. So I can claim that angle BAD is greater than the whole, or the whole, which that is the whole, is greater than any of the parts. So I'm going to specifically say it's greater than angle 2, which then means I can also claim BAD is greater than angle 3. And that right there is by substitution. Anything that I know to be true about angle 2 is also going to be true about angle 3 because remember we proved just in part A that the measure angle 2 and measure angle 3 are equal in length. But now here's where things get interesting. Notice what my next step is claiming. I'm claiming now all of a sudden that the side BD is greater than the side AB. How am I able to do that? Well, take a look. What we just claimed, or what we just proved, is that this angle here, BAD, is greater than the angle 3 here, angle D. Well, what does that actually mean? That means I've claimed one angle in a triangle greater than another angle. Take a look. I'm looking at the entire triangle ABD. What does that allow me to do? Well, we have theorems that say if we have angles that we have comparisons of, that we know one is greater than the other, then we're allowed to compare the sides opposite of those two angles. We can compare that. So I can claim that side BD is in fact greater than side AB, right? Because what I'm looking at here is actually the converse of the anisosceles triangle theorem. That if I have a comparison of angles, then I can compare the sides opposite of them. So I can claim now that BD is greater than AB. Now there's something special about BD though. Let's look at the segment BD. BD is really broken up into two smaller segments, BC and CD. So if I took CD and added it to BC, right, CD plus BC, it's equal to the entire segment BD. Why? That's the segment addition postulate, right? I can add the two collinear segments together and they equal the whole segment. But I'm going from part F to part G here now. Take a look what happens. Something changes going from part F to part G. I change one thing. Well, in part F, I mentioned the segment CD. But if you remember from our construction, we know something about CD. CD is equal to the side of our triangle, right, the given triangle, AC. That's what we want. So take CD out and put AC in. We're just using a quick bout of then substitution. So now what we have here is that AC plus BC. Hey, wait, that's what we want, right? We want to add those two sides together, AC plus BC. It's equal to the length of BD. Okay? But we know something about BD. BD is greater than the segment AB. And in conclusion then, since AC plus BC is equal to BD and BD is greater than AB, then I can also say that AC plus BC is greater than AB, which if you think about back to our original, what we wanted to prove, the original triangle, we picked two sides, AC and BC. We want to prove it's greater than the third side, AB. And why is that true then all of a sudden? It's true by substitution. We can take BD out of the greater than relationship there and replace it with an equal counterpart, AC plus BC. And there we have it. Pick any two sides of a triangle. They will then add up to be greater than the third side. All right, so that is our proof of the triangle inequality. Now, what we're going to do then is use the triangle inequality. Okay, what we like to then call this next part of our lesson is called the triangle test. See, the thing is, you can't just work with any three sides of any three segment lengths and call it a triangle. Because what we just proved is that if you pick any two sides, it has to be greater than the third side, which means you can't just be working with any three measures. No way is that going to cut it. So what we're then going to play a game is called the triangle test. If we're given three measures, let's say they're given three segment measures, the question is, could we make a triangle out of those three? Because if I pick any two sides, it has to be greater than the third side. Okay? Now, how do we then narrow down this? Because I don't want to just pick any two sides of a triangle and add them together. We're going to narrow down our triangle test a little bit better. Here's how we're going to apply it. If we then sum the smallest of the two sides of a triangle, so if let's say I give you three segment lengths, you're going to pick the two smallest segment lengths and add them together. If the sum of the two smallest segment lengths is then greater than the largest length, then that means the triangle exists. We can actually make the triangle, because if the two smaller segments add up greater than the third length, well then any other sum will work as well, because the third length is the greatest side. Added to any of the other two smaller sides, it will be greater than the other smaller side. So the trick is to just check it with one sum. Add the two smallest sides together that are given, and if it is greater than the third side, the third length that's given, then you can make a triangle, which means it passes the triangle test. Okay, so you add the two. If it is greater, then yes, you got yourself a triangle. If you add the two and it's not, then you don't have yourself a triangle. Let's take a look at an example. So can these three measures make a triangle? Meaning I have the three segment lengths, 3, 8, and 5. Well, the test, remember, says pick the two smallest, add them together. It's got to be greater than the third. Okay, so the two smallest segments that we have here are a length of 3 and a length of 5. Let's add them together. We get a length of 8. Well, compare that then to the third side. Is it greater than the third side? No, 8 is not greater than itself, which means can we make a triangle of this? No, we can't. Okay, we can't make a triangle because a segment of 3 and a segment of 5 actually add up to the segment of 8. So we'd have essentially 3 collinear points. That does not make a triangle. It just makes a long segment. That's all it does. Okay, that's not a triangle. Let's do that again for another example. Let's pick these three sides, 12, 18, and 8. Again, the test says pick the smallest two sides, add them together. If it is greater than the third, then you got yourself a triangle. So the smallest two sides in this case would be 8 and 12. Add them together, we get a length of 20. Now compare that to the third side. Is 20 greater than 18? Yes, it is. Which means, can we make a triangle with these three lengths? Yes, we can. Okay, it passes the triangle test because it satisfies the triangle inequality. Pick any two sides, add them together, it will be greater than the third. It satisfies that. Now let's say we play another game. In this last game we're going to play, it's called the range of values game. What if we're only given two sides of a triangle? Well, if we're given two sides of the triangle, we can then determine what the range of possible side lengths are for the third side, because it can't just be any side. Remember, it still has to satisfy the triangle inequality. So I can't just pick a side length of 100 here and claim that this is going to make a triangle. It can't, okay? There is a bound for this third side. There's going to be an upper bound and a lower bound. Let's take a look at how we actually can solve for this range to find our value of our third side. Well, let's call the third side S, okay? Which means S is going to be some value for the third side. But we have to remember that this third side, it still has to help satisfy the triangle inequality with the two sides that are given. The two sides that are given are 5 and 17. Meaning, let's assume then at one point that 17 is not the largest side, okay? Which means if I add 5 and 17 together, there's going to be a third side that's longer. Well, that means that third side can't be too big, because the sum of 5 and 17 has to then be greater than the third side. In other words, we can find our upper bound to this very quickly. We simply just add the two values together. So add the two sides that you're given together. That's going to give you your upper bound. But now we can then assume, what if 17 is the largest side? Which means this third side that we have missing, if we add it to 5, it also then must be greater than 17. So there's a lower bound. And to find the lower bound, it's very simple as well. We want to find the positive difference between the two sides. So I'm going to do 17 minus 5. That's going to give me the positive difference. So I know then I will get an upper bound and a lower bound. So to find then this range, I add 5 and 17. I get a length of 22. And the lower bound, I take 17 minus 5, and I get a length of 12. This right here is a range of the possibilities of the third side. If I pick any value between 12 and 22, not including them, then it will satisfy the triangle inequality. But if I pick a value outside of this range, it won't work. Think about it. Let's say I pick the value of, I don't know, 25. If I add 5 and 17, it gives me 22. Is that greater than 25? No. Okay, it then doesn't satisfy the triangle inequality. Let's say I pick a side less than 12. Let's say it was 10. Take 10 and 5, those are two small sides, add them together, it's 15. Is that greater than 17? No, which means the value of S has to be within this range to then satisfy the triangle inequality. Let's then look at a generalization of this last game. What if then I give you two sides of a triangle A and B? What then would be the possible range values for the third side? Well, here's what the generalization looks like. To find the upper bound, still very simple. We add the two side lengths together. Okay, A plus B, that's going to be the upper bound. But the lower bound, we have to do one little thing to make sure that we don't end up with negative values. Because I don't know which is the bigger side, A or B, which means if I subtract the two, I could end up with a negative value. How do we fix this? We throw some absolute value symbols around it. So this would then be the generalization when you are asked to play the range game of what's the range of the third side. So if I give you two sides of a triangle, simply add them to get your upper bound, and then subtract them to get the positive difference for your lower bound. And that is then how we can find the range of the possible values of our third side. This comes to the conclusion of our 5.4 lesson. Be sure to work on the 5.4 worksheet. If you do have any questions, do not hesitate to email me. With that, be good and do good.